Okay, we're going to get started. Welcome to our panel. This is a panel where we're going to talk about embedded processors versus discrete processors. This panel is sponsored by Actel. They recently introduced their Smart Fusion. If you're not aware of it, you might want to check it out over in their booth. And I'm sure Max will be extolling the virtues of embedded processors as we go along. My name is Rich Nass. I'm the director of content for E-Times. We starting already?
Nice.
Okay. Over on the right, on your left, we have Max the Magnificent. Max, show me your badge. Max the Magnificent.
It must be true.
Max, say a few words about yourself. What's your how do you know about embedded processors?
He doesn't know anything about embedded processors.
You put me on the floor now.
Time's up.
I think I've made my
Three
point.
months to do this.
How do I know about embedded processors? When I started designing, I was designing mainframe computers. This was years and years ago, and over the time, we went down to microprocessors and then to embedded processors, embedded systems. We didn't even have the term embedded system when I started out. We still don't know what it means. I've still not heard a good definition of an embedded system. But embedded processors for me now, my position on this is that if you're going to have a processor in your embedded system, then it's a very good idea to put it inside an FPGA rather than buying a discrete processor, as Jim would argue.
Okay, hold that thought. We'll get into that. And then we have Jim Turley. What makes you an expert on discrete processors?
So if it's Max the Magnificent, then am I Jim the Well-Endowed?
No.
Jim. Okay.
But thank you for asking anyway.
PG-13 is about as far as we go here, okay?
How can you answer that with such certainty?
Yeah, you answered that awfully quickly.
I'd prefer not to say.
You're
Do I have a mute
you're not
button
even
on
my
his
Facebook
mic?
friend.
Well, now we know why.
What was the question? What's an embedded processor?
No.
We're in the middle of ESC. This guy's the chairman of ESC asking what's an embedded processor.
The question was, what makes you an expert on discrete processors?
Oh, that one's tougher. Well, an embedded processor, by my definition, is any processor not in a PC. So embedded is sort of defined as what it's not. It's not a PC, it's not a workstation. It's sort of like defining the population of the world as all the people who aren't astronauts. Okay, that pretty much includes everybody. So by the same token, most processors, 98% of all the processors made are embedded. Right, 98% of them. Only 2% of all the processor chips made go into PCs, workstations, Macs, what have you, the sort of things that our parents
Well,
would
hold
recognize.
on. Make sure we get our definitions right, because we're thinking of something different.
All right.
We're talking about a processor that's embedded. We're not talking about an embedded system. We're talking about an embedded processor.
Right. Right. A processor used in some sort of embedded application.
No.
All right. A processor embedded into a chip,
Yeah.
like an FPGA.
Yeah.
Ah.
Now we're
That
talking.
we can do.
Okay. So you're on the side that's not the processor embedded in the FPGA.
Yeah.
You
Embedding a
got that?
processor in an FPGA is
Okay.
a terrible idea.
Says you.
He's the expert. He should know. Okay. Whoa. Where'd my slides go? Oh, okay. Anyway, okay. So that's what we're going to talk about here. Should you have your processor embedded in an FPGA, or should you be using a discrete processor, like all the processors that are out there, the atoms and the powers and the arms and things like that? Okay. I'm going to start off by asking these guys questions, and then I really want to hear what you folks think out there. So you're welcome to ask questions. Okay. So let's start with an easy one. I'll give you a softball, Max.
Thank you.
Why would anybody want an embedded processor, a processor embedded in their FPGA?
There are numerous reasons, really.
Let him finish.
Yes.
I thought he was.
Again, I think I've made my case.
Ipso facto. Thank you for coming.
Well, everything is application dependent. There are no hard and fast rules here. One of the applications, I was just over at the Actel booth, and one of the big things that they're using their new Smart Fusion device for is motor control. Motors are horrendously inefficient. And if you put an active intelligent control system on them, you can cut down the power consumption by up to 80%. If you use a discrete processor to do all of the computation and everything, you have to have the processor, you have to have memory, you have to have the analog components. You end up with a fairly large system. If you've got you don't usually have a system that's got one motor. If you're talking about a robotic system, you could have 4-axis controllers, you could have numerous motors all over the place. Each one of those is going to need a separate dedicated microcontroller plus the analog parts plus everything else. You can control 16 motors with a single Actel part. With the embedded Cortex M3 hard core, 10 million gates worth, plus the programmable analog, plus the programmable digital. That's just one application, obviously, and I'm sure Jim will come back with counter-arguments against it, but that to me would be a compelling thing. If I have to control 16 motors and I can do it with one chip, or I require 16 dedicated microcontrollers and 16 analog systems and everything else, I'd take the single chip solution.
I would love to debate this with you, but that's why we have Jim.
That's my job.
Okay. Do you want to respond to that, or do you want me to ask you another question?
Oh, fine. Go ahead.
Well, my question would be, why would somebody want to use a discrete processor?
Oh, for me.
For you.
Because it's the right thing to do. So, we have a lot of different types of devices in semiconductors, right? We have DRAMs, we have SRAMs, we have flash memories. We have
Talking to the thing.
speaking to the microphone, she says. You've got different kinds of devices. Analog to digital converters, DRAMs, memories, processors, FPGAs. We make a ton of different types of semiconductors, each one for its particular use, right? You're all with me so far. This is the easy part. One of those types of device is a microprocessor. There's a reason we make microprocessors as distinct specific devices. They're not like DRAMs, they're not like ADCs, they're not like DACs. Processors are really complicated. In fact, processors are one of the most valuable things humankind has ever created. Ounce per ounce, an Intel microprocessor is far more valuable than gold. Ounce per ounce, an Intel processor is worth more than a Mercedes E-Class, more than champagne, more than whiteout, even more than the ink in my inkjet printer, and that stuff's really expensive, ounce per ounce. But that's not true of other semiconductors, right? That's not true of DRAMs, it's not true of DACs, it's not true of other semis. There's a reason microprocessors are really, really valuable, is because they're really, really complicated. And to work well, you need to fabricate them in the right type of silicon. You need to fabricate them in a logic process, the same way you need to do DRAMs in a DRAM process and FPGAs using a mixture. So to get a good processor, you need to fab the processor in a traditional logic process. What you don't want to do is make your processor in something that wasn't designed for that. You don't want to do it in a DRAM process. You could kind of make it work, and it would be sort of interesting from an engineering point of view, but it would make a miserable processor, very space inefficient. Likewise, if you take a traditional FPGA, now not one of the new ones like Smart Fusion, but something like a traditional FPGA that's nothing but SRAM programmable gates, something you might get from one of the big generic FPGA companies, you can make a processor work in that kind of programmable logic. We've all done it. As a college student, it's a cool thing to do, but it's kind of like making a pig dance. It's not pretty and it annoys the pig. So by the same token, you can do a processor in the programmable logic of an FPGA, but it's very slow and very power inefficient and very expensive. You're much better off taking that same processor and putting it in a real logic process, which for the last 40 odd years has been as a standalone chip. Just now we're starting to see real live hard processors also integrated with other things like FPGAs on the same device, things like RAM or ROM on the same device, things like analog or peripherals on the same device. And when those processors are done in a hard silicon process, they're done as proper logic processors, you get a great CPU. But putting a processor into the programmable logic of an FPGA, not a good idea.
Again, it sort of depends on what you're intending to use the processor for. I agree that if I were trying to create the equivalent of the latest Intel chip, I would not do that using programmable logic. You talked about it being very inefficient if we put it into the programmable fabric. A typical or traditional von Neumann processor is the most inefficient thing on the planet for performing computations.
Which is why they're so successful.
Well, they're performing very boring computations. If you're running a processor at 2 gigahertz, an Intel processor, and you're doing algorithmic type processing, you're much better off putting that in programmable FPGA fabric. You can run the clock much lower frequency, you're much more power efficient. If you take that processing away from the von Neumann CPU, which is inherently not good at it, then you don't need that power in the CPU. When you're using a soft core in the microprocessor, you're not using the soft core to do algorithmic processing. You leave that to do the decision making. Soft cores are really good at if then else, the overall control.
Right.
So again, it depends what you're trying to do.
So you're saying take out the processor and replace it with dedicated logic or programmable logic in the FPGA. Yeah, you can replace a processor and software with logic. You can replace it with 7400 series gates. You could replace it with FPGA gates. You could replace it with some sort of dedicated logic. Mm-hmm. But now you don't have a processor anymore. Now you've got hardware doing some specific task. Now it's not programmable. Now it doesn't have software bugs. Now it doesn't have compilers. Now it doesn't have all the wonderful things we've grown up to know and love. Processors are inherently flexible. Yes, they're inefficient. Yes, you look at the power they consume for the job they do. They're terribly inefficient, which is probably why we like them so much. But they're great savers. They're great at conserving the one resource that's most valuable, and that's the engineer's time. So processors are easy to program. Programmers are easy to hire. You can't swing a dead cat in the valley without hitting a programmer, and probably should. Programmers are cheaper to hire than hardware engineers. They don't need to be trained. Pretty much every high school kid knows how to program in some language or other. It's just a whole lot easier to solve problems with software than it is to solve them with hardware. So that's why people throw processors at problems, particularly why Intel throws processors at problems.
Well, the problems that Intel throws the processors at are the notepad-type computers as opposed to embedded systems. You talked about the versatility of the off-the-shelf processor. You're limited to what's available off the shelf. Now, I agree that there's a baffling array of parts off the shelf. If you look at all the different vendors, the NXPs, the Atmels, and so on, it's like having a huge shopping mall of parts, but you're still limited to what's there. You pick one, you get what's inside it. If you use a FPGA, you can customize the processor with the peripherals you want. If it doesn't have something that you need, add it in.
Well, an FPGA is kind of like a big Etch-a-Sketch, right? I mean, you can turn the knobs and dials, and you can create any picture you want, but it's not a very good picture. It's not in color. It's not 3D. You can create a picture. You can do a half-assed job of anything with an Etch-a-Sketch, just like you can with certain types of logic. If what you want to do is solve a processor problem, get a damn processor. That'll do the job. Now, if you want an FPGA next to it or even on the same chip as that, something like SmartFusion, where you have a processor on the same chip as an FPGA, which is also on the same chip as some analog componentry, that's great. They're cohabitating. You get all three kinds of logic. But at least the processor on that chip is a real processor. And you get to leave the FPGA fabric for...
You're making his argument. That's an embedded processor.
Oh! Well,
I wasn't going to mention that till later.
but apart from that, but to use a generic FPGA to implement processor logic is sort of the worst of both worlds.
Again, it depends what you're trying to do. A lot of people...
Yeah, if you're trying to waste money, you're right, it works really well.
If in your system you need to monitor a big red switch, and if someone presses that switch, you need to turn the light on, you do not need a dedicated processor. A little 8-bit processor implemented in soft fabric, which takes a couple of pennies worth of the FPGA's cost, is actually way more efficient than buying even an 85-cent processor off the shelf.
Yeah, but the 85-cent processor or 5-cent processor. I mean, you look at the processors we get in musical greeting cards now. I mean, they're so inexpensive we throw them away. The battery connected to the processor is literally more valuable than the processor itself. So when processing power is that cheap and that ubiquitous, why not throw it at every problem? When you have a hammer, every problem looks like a nail. We've gotten to the point where processors are so cheap and ubiquitous, we throw processors at every problem and then write code for it, and it works.
It does, but like you say, if you get your musical Christmas card, which tends to be very annoying after a time, and it doesn't work, you throw it away. If you take that processor and put it on a board, you've added a new point of failure. The whole thing about it that's driven the success of embedded systems over the years is integrating things into smaller, fewer and fewer devices.
Right.
And if you can ultimately get the process, again, it depends. If you don't need a processor that can do extremely a lot of computations very quickly, use a soft core. If you do need a hard core, then use a device like the Actel, or Xilinx just introduced a new device, or they've announced a new device today. They don't call it FPGA. They don't want you to think of it as an FPGA with a hardcore embedded in it. They want you to think of it as a processor with configurable hardware, which just happens to be FPGA fabric. So it's a new class of device, really. It's an ARM dual-core, ARM9 dual-core, instruction cache, data cache, L2 cache, all the hardware peripherals, and then you've got programmable FPGA fabric as well.
Hardcore. I'm all about hardcore.
Again, that would be, and to me, and then you've embedded the processor in the FPGA. And it's better to do that than to go off and buy a discrete processor.
I don't know. I remain unconvinced. What was the next question?
All right, I got another question for you. You talked about how you can find any high school kid who can program a processor, and I definitely argue that. Let's talk about the learning curve. What is the difference in the learning curve from an embedded processor versus a discrete processor?
Oh, discrete processors, you got more choices. There's something like 100 different processor architectures available, 8-bit, 16-bit, 32-bit. If we're counting instruction sets, there's over 100 different instruction sets. So if you're an assembly language programmer, everything's out there. Or if you're programming in C or, God help you, Java, something like that, you don't even need to learn all of those. But it's so easy to hire programming talent. I mean, right? Software development is kind of like poetry. Anybody can start it, and there's really no hurdles. Hardware design is more like architecture, where you need a degree, and you need to go to school, and you need to learn, and you need to have really expensive tools. Whereas in software development, you get people just dabbling, and yes.
These people are software people. You just insulted this guy.
Not at all.
Okay.
No.
Just want to do a little reality check
No,
here.
that's no slight intended. And I'm behind the table anyway. So. And the exit's that way, right?
Go ahead.
So,
continue.
Having a programmable solution, having a standalone processor, having your choice of processor gives you an enormous amount of freedom to choose whatever instruction set you're comfortable with, whatever tool chain you're comfortable with, to solve the problem in whatever way is most comfortable to you as an employed or unemployed engineer. The more hardware-centric the solution becomes, the less freedom you have, right? You're limited to the hardware resources on the device, whereas if you have a processor-based solution, everything becomes a software problem. And everything becomes fixable in software and field upgradable in software and so on. So,
but also everything runs much slower in software than it would do in hardware.
yeah.
Max, you got to speak up a little bit.
Oh, sorry. It sounds loud where I am. What? Stop pointing at the back. Where were we?
You were saying something stupid, I think.
I remember.
So that reminded you?
Yes.
Oh, that's right.
Learning curve, Max, learning curve.
I was thinking of the stuff that the Impulse C folks do, where you create an algorithm in software. Basically, it's ANSI standard C. They've got a library of functions that you can use to serialize or express serializing or parallelizing. You run it with a standard C compiler, you profile your program. When you've decided from the profile that you want to accelerate this function, this function, this function, you tag them, press the go button. I can't remember what their compiler's called, but it takes those functions, it converts them into RTL, it runs them through synthesis, it loads them in an FPGA, it modifies the remaining C to put the calls into the FPGA, totally transparent to what you're doing, and accelerates by up to 1,000 times. It's the solution they've got at the moment fits on a little rinky-dink card about the size of a quarter that fits in the PCM-CIA slot of the PC. So if you're a software developer working on, say, a computer vision algorithm, and you're working on your notepad and on an airplane, and it's going like a dog, it's 1,000 minutes to run one simulation, you can speed it up 1,000 times. Suddenly you can rerun the whole thing in a minute. That becomes very significant. You're taking the hardware complexity away from the programmer, but you're giving them the ability to accelerate the code in hardware. You now take something like the Altel part, where you've got the hard processor on the chip and the FPGA fabric. To me, it's the next logical development where, yes, you've got lots of great software programmers around. They may not be familiar with hardware. Software programmers typically find it difficult to think in terms of concurrency, whereas hardware engineers find it difficult to think in any other way. But if you can give somebody
I
the
just
ability,
found it difficult to think, but okay.
the difficulty is if you give them the ability to be able to take the C code and move part of it into the hardware transparently. Again, that comes back to how ideal to have a single chip that's got the processor core in there, the RAM, and the hardware fabric that you can configure to do anything you please incredibly quickly without using a very inefficient off-the-shelf processor core.
But there's nothing about that precludes a standalone separate processor. You could still have that configurability and the customizable hardware in a separate device. It is a very charming fairy tale, I agree, but there's nothing inherent in that requires it all to be in the same device.
No, there's nothing inherent, but if you have a choice of going out and buying a single device that's got everything in it, or going out and buying one FPGA that's got the hardcore and the programmable fabric, or going out and buying programmable fabric and an off-the-shelf hardcore discrete device, and putting two chips on your board, why wouldn't you go for one chip?
What if I want to change my processor? I can't do that if it's inside the device.
Why would you want to change your processor if it's working?
I give up. Why?
Anybody daring enough to ask a question?
Who's this guy?
I got it from Walmart.
I thought so, yeah.
Any more questions?
Go ahead.
It seems like the obvious question here is, depending on what your volume is of what you're going to end up designing, a lot of us build higher volume products and the bottom line is
Don't answer the question yet.
The question here, let me just catch up. A lot of people are building very high volume products, and it is the bill of materials cost that's the important driving factor.
So it seems like everything you're saying is really good if you're building only one, and it doesn't matter how much it costs.
Everything who's saying, me or him?
The dimension of cost is, I haven't heard you address it, and what got brought into the discussion.
We're talking about the issue of the cost as you go into high volumes. I mean, I think where you're going with this, most people think that you shouldn't be using an FPGA when you go into very high volumes. Is that where you're headed?
Well, this is what I'd like to hear your arguments on your side of how does cost figure into this.
Okay. Where does cost figure into the equation?
Again, that one of the problems we have here is that there's such a large application space. There are FPGAs available that are sub $1 or around $1 value. You cannot put those do not come with a hardcore processor, and you're not going to implement a superscalar 32-bit processor in those. There's not enough fabric. An 8-bit microprocessor, yes, you can put that there with fabric to spare. One of the things, and yes, you can buy discrete processors for like 25 cents. When you talk about bill of materials, we're happily in a point of time where there's been an upswing. We're starting to see more people spending money, more projects going ahead. If you've got a bill of materials with 100 parts and there's shortages in one area or another, that becomes very painful to you. If you've got a bill of materials that's only got a few parts, it's a lot easier to deal with, assuming the suppliers of those few parts, and I'm sure Actel will be delighted to supply lots of them.
Standalone processors are manufactured in such humongous volume, particularly the popular ones, well, by definition, the popular ones, that they're dirt cheap. As we said, they can even be cheaper than the battery that powers them. They can be cheaper than the printed circuit board you solder them to. So if cost is an issue, usually your overriding concern is to piggyback on someone else's volume. It's difficult to plead your case within a semiconductor vendor and say, oh please, I need you to cut the price of this chip in half. What you do is you go out and you find the world's most popular chip, and you just design your product around that. For a lot of 32-bit embedded systems, that means you design your system to look as close to a PC motherboard as you possibly can. Not because that silicon is simple, because it's not, but it's because that silicon is an extraordinarily high volume production. And so you just piggyback on that volume and wind up buying processors and core logic and Ethernet interfaces and graphics chips and whatnot for cheap, because there's a whole bunch of PC companies buying the same thing while you're buying onesie twosie. The same is true as the embedded space. You pick really popular 8 or 16 or 32-bit embedded processors and just live with it and say, well, it's maybe not the processor I would have picked because I prefer instruction set X, or I prefer vendor Y, or I prefer tool chain Z. But yeah, if you're going for lowest cost, just pick whatever is selling the most of and get some of that.
Max, I hope you're going to tell us why that's so inefficient.
Well, again, it's a very much an application-dependent thing. There are more costs than just the cost of the chips. There's the costs of, I agree, it only takes a few cents to put another chip on the board. There's the area of the board. There's power. If you've got a discrete processor that's talking through the wires on the board to another component, that uses more power than having the device on the same chip. There's costs in terms of reliability. Every time you have a solder joint on the board, that's a single point of failure waiting to happen. And I know that modern processors are inherently
Good.
Well, pretty darn good compared to the way they were, when I started out. When the scalpel was you could see somebody walking around with a scalpel, you knew there was a problem on the circuit board. But it's still a point to consider. The more solder joints you've got on the board, the more points of failure. The more components, the bigger the board, the heavier the board, and so forth. And if you can squeeze it all in one chip, I would say it makes sense to do so.
Okay. We have more questions?
As opposed to the ones we've been making so far?
More theoretical. I've been developing firmware the last 15 years mostly.
Can we give him a mic?
Yeah.
Come up here.
Would you mind stepping over to the microphone? We're assuming the microphone's on.
Hello? Okay.
There you go.
So I've been developing firmware for the last 15 years for hard processors, and the last year and a half for the Xilinx Microblaze soft processor. And, just to the gentleman in the middle, the comment I would have, and that's you.
There's no gentleman.
And
he's
I'm not
a good
in the
guy.
middle.
He's a good guy. Now, as we all know, designs change, even in the middle, and sometimes you say, oh, we got to do this, and we have to add a serial port, and going with the soft processor is just invaluable in a situation like that.
I like
it is.
So wait, how does adding a serial port help? How does a soft processor help add a serial port?
Well, you can do it dynamically, and if the board is designed in a general way with I/O, if you know that things are going to change, sometimes they won't, but it depends. It can be real helpful, but on the downside, the problem I've seen with the soft processor is that we all make bugs, and so now you're dealing with the FPGA designers' bugs when you're dealing with a soft processor, and whether it's in the way that they sort of inserted the soft core, and I think that although you can have hardware bugs in a hard processor design, I felt like going with the soft processor in some cases probably has lengthened the development cycle to some extent. The other problem...
See?
But before that, he said that it was very useful to be able to change the functionality
But
and
before
add
that,
stuff.
before that, his point didn't make any sense. So this is what I'm
Then he didn't have a microphone.
The other problem, and I think this will probably go away shortly, is that in my experience, the design tools for the soft processor, at least in the Xilinx case, are much less mature than those for the for the hard processors, although Xilinx has come a long way in the last year and a half.
Immature
so-
tools.
So
You've
I just
probably
want
heard that a lot.
I don't want to take up your time. I just wanted to add that and see if you have any comments.
That's
Nope,
a good
I
point.
think
We
you're
should
on the
talk
right
about
track.
the
Well
tools.
done.
No, it's true. We should talk about the tools, and that is an issue. That the tools for the discrete processor have been around for a long, long time, and they are mature, and that's not necessarily the case with the embedded processor. Max?
Okay, well, I can't speak to all the different tool sets because I don't know all of them intimately. The one that I became most familiar with recently was the ARM thing. The Actel device. And I'm not like waving the Actel banner and singing the Actel song. I just wrote an article about it. It's not my fault. I didn't put that up there. With the way the Actel folks have tried to do it, they've tried to say, okay, we've got a single chip. It's got FPGA fabric, and obviously hardware designers are better equipped to deal with that. It's got a hardcore processor, the Cortex M3. Software guys are familiar with tools like the ones from Kiel and so on. So they've gone outside and made relationships so the software guys can use the tools that they're familiar with using. They've got a bridging piece of software that links the two domains. So for the sort of applications these things are targeted at, like industrial control and things, very often it's going to start with the software guy who's going to define register port maps and various other things, and the interfaces he would like to use or she would like to use to talk to the underlying hardware, the FPGA fabric. They can do that, and they can export that register port map across the hardware guy. So now he's got a defined interface to work to. Use the same bridging interface to configure the analog software and everything else. So that sort of keeps things separated. And using established tool chains that the software guys are already familiar with using makes a lot of sense to me, rather than trying to develop in-house stuff as an FPGA vendor where you're not really well equipped to that. Like I say, I couldn't talk to all the different tool chains because I'm not all that familiar with them.
But I will. Tools are the most important thing. Tools sell the processor, not the other way around. At Embedded Systems Design magazine, they do a survey every year of all sorts of embedded designers across the world. And one of the many, many questions that appears in the survey basically boils down to, how did you choose the processor that you're using now? And overwhelmingly, the answer was, I chose my tool chain first, then I picked a processor supported by that tool chain. And the first time I saw that, I thought, that's crazy. Why wouldn't you choose the processor first and the tool chain second? But the more I thought about it, the more it makes sense. You use the tool chain first, and then you choose a processor supported by your preferred tool chain. And it makes sense because if you think of software development or even hardware development as being like a carpenter, right? Carpenter uses his tools, he's got his hammer, his saw, power tools, what have you. You can change the type of wood. You can change the carpenter's workpiece from mahogany to pine to balsa or whatever. That's okay, but you don't change the tools that he touches. You don't take away the hand tools. You don't change the things that you touch. And likewise, as a programmer, programmers as a rule are okay with changing the processor, but not the tools that you touch. Because every day you come down, you sit in the cubicle, I touch my compiler, I touch my debugger, I touch my code profiling tools. Don't change those, because that's where my skill set lies. So programmers, as a rule, become very attached to their tool chains, and then they choose a processor that's supported by that. So the tool then becomes paramount in importance. And you want, as a processor vendor, you want to be supported by as many tools as possible. And as a tool chain vendor, you have more of a lock on the customer than you might think you do. So how does this play into standalone processors? Give me a second. Because there are more standalone processors, you have a bigger selection of tool chains, which are in turn more well established because standalone processors have been around forever, whereas embedded ones have not. So you've got a wealth of tool chain choices which have been around longer, are debugged, are more popular, and you can hire and fire engineers who have that skill set. How's that?
So you're advocating a way to hire and fire software engineers?
I'd hire them all. They're adorable.
No, I totally agree about the tools. Tools are very important, not just for software guys. Hardware guys use tools too. And the bottom
Usually a
line is
big
you're
hammer.
comfortable with whatever tools you've been using for a long time. I hate it every time Microsoft release a new version of Word. All the bloody controls move around. Things that I used to be able to do easily last time, like formatting a paragraph, now it takes me half an hour to find where the tools disappeared to. So, yes, I don't want to move tools just to write another article for this magazine, then move tools to write an article for that magazine. That would be why the companies who are now embedding, obviously if you've got your own soft-core processor, then I don't know if you use external tools for that or if you use your own internal tools. But when you're doing things like the Cortex-M3 for Actel or the Cortex-A9 for Xilinx, you do not go off and write your own tool set. There are a huge amount of tool chains out there that already support those processors. You'd be insane not to make those tools available to your users. So the users, and the Cortex-A9 and the Cortex-M3 are two of the most widely used processors in the world. Now you've just augmented them with the ability to add customizable hardware.
Yeah.
Oh, that sounds pretty good.
Thank you.
It's almost believable, isn't it? Yeah. And his lips move and everything. Yeah.
Let's let this guy ask a
He's so
question out
lifelike.
here. Step up to the mic, please.
My mother will be so proud.
I spend about 30 to 40% of my time and about 75 to 95% of my stomach lining on issues that do not behave the way the documentation says they're supposed to. It's a big deal if a microprocessor, for example, or any component doesn't do what it's supposed to do, doesn't do what the documentation it says it's supposed to do.
So it sounds to me like the problem is in the documentation.
That's one way to look at it, but
Jim,
if you're at
do you
the
use
other
the right
end,
documentation?
if you're at the other end, it doesn't make you're stuck either way. One time in particular, I lost 2 months to a microprocessor, which I won't name, that ended up having jitter in the system clock, rendering one of its blocks incapable of operating according to specification. The jitter varied from instance to instance, so I ended up qualifying the microprocessors before they went in the product, one by one. When the discussion came up of the different processes used to create the FPGAs and the microprocessors, what I was told about that particular issue was that the analog process used to create the system clock, to generate the system clock from the crystal, was a different sort of process than the one used to create the microprocessor. And by putting the PLL for the system clock in together with the digital part for the microprocessor, the manufacturer had decided to compromise on the analog part, on the PLL, and therefore the PLL had tremendous jitter that in turn compromised the microprocessor part. Is this something that...
This is going badly for you, Max.
Actually, I was thinking that for you.
is this something that people who decide to use a mixed process part, or a part that should have mixed process anyway, need to be aware of things not working the way that they're supposed to?
But one thing I would point
I
out
think the
is
takeaway from that is don't believe the documentation. Well, they don't read it anyway. But.
one thing there though is that I think you were talking about a microprocessor, and the only analog portion was the phase lock loop or the clock generator portion. But I don't know. Maybe you know this, Jim. In embedded systems, what proportion of processors in embedded systems are pure CPUs, as opposed to microcontrollers that have analog inputs and so on? In which case, you've already got analog in there. You can't help but mix them in the same chip.
I know the answer, but it'll cost you.
How much?
Yeah.
Rich will pay.
That's right. In microcontrollers especially, you do get mixed features. In fact, analog is becoming more and more common on what were nominally digital chips. But really, it works a lot better than it used to. I would just stay away from his processor.
What works better than it used to?
Mixing technologies.
Mixing different kinds of process technology. It used to be very tough to mix things like SRAM cells and logic circuits and analog circuits, and you had little old ladies with hairnets and X-Acto knives trying to get everything to work, and it was very much a compromise. But Nowadays, people are getting pretty good at embedding analog circuitry on digital devices. It's not nearly as scary as it used to be.
Did we answer his
that doesn't
question?
sound like a documentation problem per se. It just sounds like a not very good design of a physical chip. And that will teach you to buy off-the-shelf microcontrollers.
Next up.
So we're moving on, huh? Okay. Another question.
Hi, I just want to give my own experience on this from about 6 years ago. And what we needed was a power PC, a fast power PC, and also a reasonably medium-sized, small to medium-sized FPGA. And so one of the solutions, which is the one we finally adopted, was to go with this $10 power PC, very nice part. And the Xilinx chip was like a $17 chip. Now, we could have gone with a Xilinx part that actually included PowerPC on chip, but the cheapest one was like $100. So unless the manufacturer provides a solution that has a reasonable price point, it's really not practical. It wasn't practical then.
So how did $10 plus $17 become $100? And that was exactly your problem, right?
Yeah. Yeah, well, the problem was one of them was, the cheap one was what is the Spartan series. The Spartan series, I would say, well, we'll take a technology from 2 years ago and we'll sort of cut it down to, and make it in huge quantities, we'll save a lot of money. Whereas the other one was, here's our latest and greatest technology, the one that we want to get a lot of profit margin on.
Yep. That's how that works.
Yep. Now, Xilinx would like me to say sorry, and they won't do it again.
But is it fair to have
I
the
think they learned
discussion
their
about the
lesson on that one.
processor from 6 years ago?
Well, no, it's a valid point. In the past, I think the way things were perceived a few years back was that if you were going to be buying an FPGA, and these are large, big, hairy FPGAs with 1, 2, or 4 power PCs on them, that you could charge a premium for that sort of thing. And it was because it wasn't being used in a typical embedded system. It was being used in a design that would be made very few times, and people would spend a lot of money for those. Where things are going at the moment, like Jim said, there's computers everywhere now. There's computers in everything, even Christmas cards and annoyingly musical socks and things. And so people are addressing that. The FPGA companies are addressing that by bringing out parts that are only a few dollars. And like again, Xilinx haven't released pricing. I don't know if you've heard anything on the device they announced today, but I personally am expecting it to be in the like $5, $10 region. And this is with a dual-core Cortex A9 and the configurable FPGA, and it looks like it's going to have analog as well. Now, for $10 for everything in one device, that to me becomes a very compelling thing. My understanding for the Actel parts, and again, this isn't something they've told me, but I think that you're talking about $3, $4, $5 for one of the Smart Fusion devices with the analog, digital, and Cortex M3. I could be completely wrong there, by the way.
Okay, so what would the discrete solution cost? Similar performance?
Well, you wouldn't get similar performance. See, that's the point. Is you'd get better performance, you get more flexibility, you get more freedom to choose your own tools.
But you don't choose the tools. You start with the tools and you use that to pick the.
See, exactly. So, by the same token, people like to pick their television set separate from their DVD player or VCR. Companies have been making TVs with built-in DVD players and VCRs for a long time because it seems like a perfect pairing because you always have one plugged into the other, and yet people never buy them. Why is that? It's because people like to choose those things separately. I like to upgrade my TV separate from the upgrade cycle on my DVD player or my VCR. I know I'm going to plug them in next to each other. I know they're going to be side by side. I know the bandwidth requirements roughly between the two. I know it makes sense to have them in the same plastic and buy them at the same time, but I don't, and neither does anybody else. So I think choosing the processor and the FPGA, or the processor and the peripherals, or the processor and the core logic, or the processor in anything, is a similar sort of decision. As an engineer, you want to make those decisions independently, and you want to be able to upgrade one separate from the other. So let's just put it down to human weirdness.
I would sort of disagree with that a little bit as well. The way it's been my experience is that once people, like you say with tools, somebody gets familiar with a tool set, they don't want to change. Somebody gets familiar with the processor core, they don't want to change. You know, if you've been using a Cortex-M3 for the last couple of years, you really don't want to change that. You're familiar with it, you know all its tricks, you know all its glitches, all its problems. You stick with what you know. I was going somewhere with that, but I've forgotten where it was going.
That's okay. None of the rest of us were paying attention either.
Okay, we got another question?
Why do microcontroller guys have the bit bang?
What was that? I'd love a beer, yes, please.
Microcontroller guys have the bit bang.
Why do microcontroller guys have to bit bang?
I don't think I'm allowed to answer that here, am I? I got scolded the last time I said something like that. I think
didn't
they
even
like
know
it.
the question. Understand the question?
What?
Oh,
Come on up.
Who is that strange woman who keeps on jumping up and down at the back?
I don't know. Bring her up here.
Go ahead.
A little case study. We did a hardcore processor in an FPGA. You use IP for connections to the DRAM controller. You can put the pins. Well, we happened to pick the pins wrong, and it turned out that the processor, the DRAM, would stop working when we changed other parts of our FPGA code. And the turnaround time was several hours each time we tried a thing. So it can be really, really bad on engineering time if the processor, you have to hook it up via the FPGA fabric.
I don't like you.
Now, on the other hand, if you have one where the hardcore processor is independent, you hook its DRAM up to specific pins, and then you have some FPGA. That might be fine. But generally, FPGAs have poor processors, and
See?
FPGAs are expensive, and
See?
But again, I think things are changing. And for example, the Xilinx part that was announced today has DDR2, low power DDR2, DDR3.
Oh, yeah.
All
So
hard, all built in, probably with dedicated pins. So that solves that sort of issue.
yeah, if they did that, great. That's not what they did before.
Well, no, they're learning, like we all are.
Well, some
And
of
again,
us.
they're very sorry. And they won't do it again.
Okay, I think we have time for one more.
You
Or
two
two
can arm
more.
wrestle over it.
Now we'll get you, don't worry. That'll be it.
I like the idea of doing some algorithms in hardware. I understand it can go a lot faster. My little bit of experience with FPGA, it seems that it took a lot longer to develop the Verilog VHDL to do those algorithms in the FPGA than for a software engineer to do just to write it in, in code. I was just wondering, was that just a bad experience that my group had, or in general, is that the case?
Yeah, I think it's just you.
No, I think it depends on, again, the experience of everyone combined. I mean, I can dabble with programming, but I'm not a programmer. If I wanted some software writing, I'll go to a programmer who was experienced in the area that I'm looking at. If I want to take an algorithm and implement it in hardware, I wouldn't go to somebody and say, right, here's a book on Verilog. Go and learn the Verilog, go and learn DSP, take this algorithm and implement it. I'd go to an expert who's already familiar with using hardware to implement algorithms. That person can probably whip it out very, very quickly indeed. Now, there's also the case that there are multiple different microarchitectures that you can use for almost anything. And it's not always intuitive as to which one will be best for the particular algorithm you're dealing with. And even an algorithm, if you change the parameters of the algorithm, you might want to use a different microarchitecture for it. And so there are tools now, the BlueSpec stuff, BlueSpec System Verilog, that lets you parameterize a high-level representation. It's higher level than Verilog, and then generate multiple microarchitectures in a few minutes and test them all for the various characteristics like latency, power, time of flight, input to output, and so forth. Again, you need some experience to use that stuff. But if you're using the right tools and you've got experience, you can generate hardware very quickly. If you give a hardware engineer the problem, say, right, 90% of this project's hardware, 10% software, go and do the software as well. The project's going to grind to a very slow halt. You put experienced people for the various areas.
What he said.
Okay, one more.
There seems to be actually a third.
You have to go up to the mic.
It's a test.
There's really a third seat that's kind of missing here, and that's the
What am I?
processor vendors that have been putting metal gates around a processor now that you can develop on a development board using an FPGA and then turn right around and within a couple of months develop an ASIC out of it through standard cell gate technology. There's at least 2 vendors I know of that are already doing that, and another major vendor that's going to be entering that market soon. It seems like a hybrid here of what we're talking about, where you have an embedded processor, an FPGA, and a hardware processor that your logic is separate. Now you can supposedly have the best of both worlds. What's your competitive analysis of those types of?
My competitive analysis costs money, but here's the quick. I'm a big believer in configurable processors. For a couple of years, I made my living selling configurable processors. So I'm a total convert, and you're right. Sometimes making small changes to a processor, like adding your own custom instruction or a couple of custom instructions, can in some cases make a huge amount of difference to performance. As often as not, it's a big engineering waste of time, but at least it's fun. But yeah, there are cases where it pays off enormously. There just, as you point out, there aren't very many companies that do that. And you do take on the burden of the tool chain, and you take on the burden of debugging. The minute you customize a processor and make it your own, you are now the only guy on earth who knows how it works, which means all the burden falls onto you. And although that's really cool from an engineering point of view, it scares the hell out of your bosses.
Didn't you used to work for an ASIC company where you argued about embedding processors in the ASIC material rather than buying an off-the-shelf?
Probably, yeah.
I just wondered.
Okay, I think that's all that
Your
we
point?
have time for. I'd like to thank these 2 guys for not coming to blows. And thank you for your questions.
You wish.
That was good fun.
Very
Yeah,
good.
it was,
Very
actually.
good.